Good morning, students. And today we'll be working on a very similar algorithm, and it's called naive Bayes using multinomial distribution. So in previously, we worked on the Gaussian distribution, and it's perfect for when your features are mostly continuous variables. That is, they have continuous values. But multinomial distribution will be perfect when your features are mostly count based. A very good example is the frequency of words. So let's take a look. Let us recall the naive Bayes equation is nothing but the probability of y given some words is equal to the probability of words given the class multiplied with the probability of y divided by the probability of w. And here, the probability of w given y previously is a Gaussian, but for multinomial distribution is nothing but simply taking the count of that particular word divided by all the available words, right? So let's take a look and take an example and see how it works. Here's an example. So let us try. So right here, I will create a data set called train. But before that, let me just make sure that I have NumPy ready. So the train is NP array. And here I have Chinese, Beijing, Chinese. So you can imagine that this is one document filled with a lot of words. And the next one is Chinese, Shanghai. And we can have four more, Chinese Macau. And next one is Tokyo and Chinese. Great. So those are the training set. And we can also create a similar one for tests. Chinese, Tokyo, Japan. Okay. Right. And here is the train target, in which we just want to classify whether this document is related to China or not. And so the MP array is basically 1, 1, 1, and 0, according to this yes, 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 and no. Right. Now that we have this train targets, we can create this count, right? So you can notice that before we can calculate the probability of w given y, we have to first calculate this equation. And this equation, we have to first count each of the word, right, in each of the class, right? So for example, we want to know how many Chinese word in the class of China, right? And how many words of, for example, Tokyo in the class that is not China, right? So let us create this. And we're going to borrow a very handy library in sklearn. sklearn.featureExtraction.text import.count vectorizer. And vectorizer equal to count vectorizer. And what we can do is simply pass in the, and we just perform fit transform on this train. And what we can get is basically a list of how many words, how many Chinese is in the in this trained array. So let's take a look. So we can first print out the feature names. How about we just run this line of code first? Feature names. right? So we can print out, so we can see that the word itself are the features now. So now these are all the unique words you can find in this training array. The next thing we're going to do is we can print the type of what we get, and that is xtrain. And we can see that this is some kind of a sparse matrix of counting. What we can do is we can convert it into array, and so we can take a look how does it really look like using this toArray function. Okay, there should be no underscore. So you can see that it could create a very nice counting matrix. So here we can see that in the first sample, there's 1 Beijing and 2 Chinese, right? So we can check, double check, 2 Chinese and 1 Beijing, perfect. So this is called the counting matrix. Now, once we got this, we can now calculate this likelihood, right? So now let us do that. So we can define a function called likelihood. In which we're going to return the sum, right? And divided by np.sum plus sum x is equal to 0, right? So in right here, this is nothing but this one, right? And it's sum across this, right? And np sum is basically you sum across all of this, right? Let me just check. So we can actually, why not we just run line by line and see how does it look like, right? But before that, why not we finish this function? So this divided by that should be okay. Now let us try running this xtrain plus 1 equal to xtrain train target is equal to 1. So now we got some samples that is only belonging to class 1. All right. And we also do the same for class 0. Okay, great. So we can now try to run each of them. So we can say xtrain class 0. We can try class 1 first. Dot sum x is equal to 0. So this is basically what we get, right? So again, before we print it out, we can see class 0, class 1 dot toArray, right? So what is this is that each of the word you try to sum it across the row, right? So you got 1 here. So it means that in class 1, there's 1 Beijing word. And similarly in class 1, there are 5 word that is actually written to Chinese, right? So this is basically this one, right? And if we refer to equation, it's basically the above one. Now we can also try it out np.sum xtrain plus 1 dot sum x is equal to 0. And we can get that is the total is 8. So what we do is okay, now we have all the number of words. We just sum them all up. So now we know that the probability of having Beijing, right, in class 1 is nothing but 1 divided by 8. Similarly for Chinese is nothing but 5 divided by 8, right? So that hopefully helps you understand what this formula does, right? All right, great. So if we can understand now, why not we try to run the function that we have defined above and see whether it works. Hopefully there will be no problem. So likelihood 1 equal to likelihood x train class 1, right? We can print it out. Great. So I think we got all the probability. So this is the probability of having Beijing in class 1, and this is the probability of having Chinese in class 1, right? And this is nothing but basically this probability that we just talked about. Great. And then we can also do the same for class 0. So if you don't mind, I just copy here and make this 0 and 0 and here 0. Great. Good. So now we got very nice likelihood. But here what I want to do is to introduce something called Laplace smoothing, which is a very simple yet a very crucial theory that you need to know. Basically, according to Laplace smoothing theory, nothing is really with the probability of 0 because we can never say that things will never happen. There's no such thing as 0 probability. It doesn't make sense, right? Even though it doesn't, it never exists in the training set, it doesn't mean it would never has that probability. So Laplace smoothing theory say that, hey, we should add at least 1 to each of the count. And subsequently, because we each want to each of the count, we should add plus n to each of them, right? So you can imagine if we add 1 to each of the word, we should plus, if here is 6, we should plus 6 here, right? So the idea is super simple. So let us implement this and making sure that we implement Laplace. So here is likelihood plus equal to 1. And now return. Okay, why not I just copy what we have written here and then just add the Laplace, right? To make sure that we don't do any mistake. Right here. And what we're gonna do here is just to change here to add a Laplace. All right. And similarly, what we want to do here is we want to add Laplace here, right? And then that should be okay, right? So now nothing is really 0 with 0 probability. Given this, now we can do, we can copy what we have done above for 1 and also for 0. And now we can print it out. Right? And you can see that now things are never 0, which is according to the Laplace theory, right? Okay, great. So I think we are able to sort it out the multinomial distribution, right? Very, very simple. That is just counting and divided by the total sum, right? Now the priors, I think this is very straightforward. So I would just copy what I have already prepared. So the idea is nothing but I just want to make sure that I count all the 1 I have divided by everything I have. And then now I can get the prior that I have 3 Chinese. So the probability of y equal to 1 is 0.75. And I have only 1 Japan, so 0.25. Now let us, it's time to actually calculate the total likelihood. And the total likelihood is nothing but taking all the words and multiply them together. The same thing we do in the previous class, in which we just take the product of all the probability. Then we can know the final probability, right? And of course, let's just split this. Because later on, once we get the probability, we need to just multiply with the prior, we get the final probability. But I don't think we should jump that yet. let us do the total likelihood first. So for the total likelihood, we can simply do like this. So PX tests. Give me 1 second. Okay, PX tests. Y1 equal to np.prob and np.power, and then the likelihood 1, and then the X test2 array. Okay, great. So now you may wonder why I'm using X test suddenly, because previously I'm using X train. Actually, the training is already done, right? Because we already create please recall that the training set is mostly for creating this distribution, right? The counting distribution, right? Now, and we also have the priors, right? So once we have that, we can now put our X tests, right? Under this likelihood that is that is retrieved from the training set, and try to see whether what is the probability of this X test given this likelihood that we have calculated using the training set, right? So let us do this, but I don't think we have X test yet, right? So let us create the test. I think we already have this test. What we can do is we can do X test equal to vectorizer dot transform test. So notice that I'm not using fit transform because I want to use the same features according to what my training set defined. So I'm just using transform. And then I think we can already show the two array. Let's see how does it look like. And we can see that, in the X test, there's no Beijing, there's a 3 Chinese, and perhaps this is Japan, I'm not sure. But anyway, we can now try to calculate this accordingly, right? So what we can do is we can take the likelihood, which is this one, and multiply with how many words each of the word I have, right? It may sound like, why do you do the power? Well, you can see that this is the X test. So this is the each of the word, right? And the likelihood is nothing but, sorry, is this, right? So if we have 0 of this, we just multiply this one 0 times. If we have 3, we just multiply this 3 times, right? Because the probability is simply the product, right? But because we multiply this 3 times, we just take the power anyway, right? So that is for those who suddenly confused, how did I jump to this power thing, right? And once I do the power, I just take the product of everything. Then I can have the total likelihood, right? So let us take a look. How does this look like? And now the total probability is that. We will do the same for, we'll do the same for 0. All right. So now we got 2 probabilities. So what does this 2 probability tell us? Well, it seems like this number is much bigger, is a little bit bigger than that one, right? So there's a higher chance that it's not really Chinese, basically it's 0, right? And I guess it makes sense because if we take a look at the test, there's also Tokyo and Japan, right? So it's very split whether it should be China or Japan. But according to our algorithm, it seems like it should be class 0. That is, it should not be really China. But wait, we have to now convert it into probability. So we need to multiply with the priors, right? Remember, that is the naive Bayes equation, right? So what we can do is we can take the py given x, py1 of x is equal to prior 1 multiply with px test y1, right? And similarly, what we're going to do is do the same with the 0, right? And I think the result would change because our prior one is much higher, right? And once once we do that, now we can print this out. So based on this, we can see that this number is much higher than this number. So we can conclude, so our conclusion is that our test sample, which is Chinese, let us take a look again. Tokyo, Japan is predicted to be actually China, right? It's China related because according to the probability is more is higher when you predict to belong to class 0, right? Oh, wait a minute, this is class 0 and this is class so 0003 00, yeah, this is bigger. Oh, and this is 1, right? Oh, I just got confused. This is 0, so this is 0, and this is 1, and this is 1. So yep, it's China. Yep, great. Please notice that there's some problem here, right? I want to fix something that is instead of using raw probability, it's always very nice to use instead of log probability, right? Log does not do anything. It would not change the meaning of the interpretation. It would just scale the numbers to make sure that the numbers are not small like this. And it's very nice, right? So for example, if I just take np.log this number, right, and np.log this number, you will see that the smaller would remain the smaller one, right? But what is very nice is so this is still smaller than this one, right? So class 0 is still win, but the idea is that it will never be some numbers like 0.00001, which will cause a lot of mathematical instability. Instead, we apply log. It will make our numbers much more stable. So that is like the best practice. So what we're gonna do is change our code a little bit to apply this logarithm. So actually, I already prepared the code, and I simply I take the X test and then apply the np.log, right? And because it's np.log, we can change it to multiplication, right? So log of multiplication is basically addition, right? So we can simply imagine that they are multiplying. And then because they are multiplying in the sum product, we can work it like a dot product, right? Which will help us make our operations very, very lean. So this is the final one. We can see that this is much higher. I'm sorry. The probability of, let us take a look. Which one is higher? This is less negative, right? So it belongs to class 0. Wait a minute. It doesn't make sense, right? Because previously it should belong to class 1. And if I apply log, it should not change the meaning, right? So give me 1 second and I will be back. Okay, I'm back. Actually, there's nothing wrong. I haven't simply multiplied with the prior, right? So let us multiply with the prior. So we can do that. The final one, y1 given x is nothing but np.log. So we can also apply log probability to the prior one plus px test y1. Similarly, we're going to do this for 0. And 0 here. And we should get our information. And we can see that, this is a much, this is slightly bigger, you can say, right? Because it's less negative, then there's a higher chance that the test set belongs to class 1, right? So let's review again what we have done is a lot, right? And now we're gonna go to the real data, right? So right here, what we have learned is that we have learned that there's a naive Bayes multinomial, and we can estimate using the naive Bayes distribution and is given by this count thing. And then we provide an example, we count, and then we perform the likelihood, right? And then we demonstrate how things are summed. We also learn about Laplace smoothing. And finally, we demonstrate how to do the priors. The total likelihood is nothing but just power of the frequency of the word. But we also learned how do we convert them into total probability and multiply with the prior. And lastly, we do the log probability to make everything stable, right? Great. So let us quickly run some examples. So here I'm preparing some news group, and I want to predict whether certain news are more inclined to certain class, right? So you can take a look, but I would just run it quickly so that you can see how things look like. So let me see. So actually I already count things, right? So everything is counted. So what I can do is I can calculate the prior. So I have a class for the likelihood, right, which we already wrote. We already also have the class for the prior. We also have the fit method, right? And the fit method is nothing but just enumerate the class and run the likelihood, right? And finally, we can have the predict function. Right? And the predict function is nothing but just take the priors, log them, and take the x-test dot product with the np.log, which is basically the multiplication. And then finally, we can now use them accordingly. So give me 1 second. So we first fit them. So let us clear off with the restart and run all and make sure that things run perfectly fine. All right, and we fit them. And now we can actually do some prediction. And finally, we can print the results out. Right, and you can see that, wow, our multinomial is pretty good, right? Because it can kind of predict things right here. And yeah, so that is the multinomial distribution for you. Please feel free to pause my video and take a look, and also take a look at the GitHub code for further understanding. All right, thank you very much, and see you in next class. Bye-bye.